All right, guys, this is lesson 9.1 sequences. Um, we're just going to look at some examples of sequences and finding the limits and determining whether they converge or diverge. A sequence is defined as a function whose domain is a set of positive integers. We look at sequences in terms. So here we have a sub 1. That means that the first term will be matched to 1, second term 2, and so on. So the number a to the nth, a sub nth, is the nth term of a sequence. So let's take a look at some examples here. First of all, we're going to look at uh, finding some terms of a sequence. So if I wanted to list the first 5 terms of this sequence, I want to list a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and so on. So whatever term I'm looking for, that's what I'm substituting in for n in the place of n. So if I want to find the first term, that would be negative 2/5. If I want to find the second term, put 2 in for n, that would be positive 4/25. If I wanted to find the third term, and so on, and so on, and so on. So however many terms you need to list, that's how you would do it. A sub 4, a sub 5, and so on. Plug those in and find the first 5 terms of the sequence. So you should find a sub 4 to be 16 over 625, and a sub 5 to be negative 32 over 3125. Now, the majority of this chapter will look at determining whether a sequence diverges or converges and being able to find the limit. So when we want to find the limit of a sequence, then we just need to treat the sequence as a function and find the limit of that function as n approaches infinity. Okay, so if I want to find the limit of a sub n equals 5n squared over n squared plus 2, then basically let's just find the limit as n approaches infinity. Now, you can use the techniques that we learned in Cal 1 or in Cal 2 in the previous chapter. So here, this is indeterminate. We could use L'Hopital's rule here and use it twice. We have 10n over 2n, or 10 over 2. So we know that this converges to 5. Okay, number 23 here, a sub n equals 2 times n over the square root of n squared plus 1. Um, we could divide by the largest term there of n. And remember that the square root of n squared equals n. So we can divide both the top and bottom, both our numerator and denominator, by n. So 2n over n. The square root of n squared is n, so I'll put n squared over n squared underneath the radical underneath each one of those terms down there. Simplify. 2n over n is simply 2. N squared over n squared is 1, plus 1 over n squared. Now, if we think about the 1 over n squared, the limit of that n squared will continue to get larger and larger and larger in that denominator, so that part would approach 0. So that gives me 1 plus 0 underneath the radical, or 2 over the square root of 1, which means that this would converge to 2. Okay, let's take a look at number 31 here. We have the sequence a to the nth equals -1 to the nth power, a sub n, sorry, equals -1 to the nth power times n over n plus 1. So the limit as n approaches infinity here, -1 to the nth power times n over n plus 1. Now, the n over n plus 1, again, if we use L'Hopital's rule there, we would end up with 1 over 1, which tells us that this approaches 1. However, -1 to the nth, if we look at the first few terms there, you quickly see that this bounces back and forth between -1 and +1. So what that tells me is that this limit does not exist. It continues to go on and on and on in that manner. It does not exist since we're multiplying it times 1 here. Just keeps bouncing back and forth, back and forth, back and forth. So that tells me that this diverges since the limit does not exist. Okay, 32 here. A sub n equals 1 plus -1 to the nth power all over n squared. Okay, so again, we've already said that -1 to the nth power is -1, +1, -1, +1. So looking at our numerator, if it's -1, then 1 plus -1 would be 0. If that's +1, then 1 plus 1 would be 2. So that stays between 0 and 2. It alternates between 0 and 2, 0 and 2, 0 and 2. However, our denominator will continue to get larger and larger and larger with each term. 1 squares 1, 2 squares 4, 3 squares 9. Therefore, the limit as this approaches infinity, since our denominator will continue to get larger and larger and larger than our numerator, which is positive or 0, will be going towards 0, converges to 0. All right, we'll also deal with n factorial in this chapter. So here we have the symbol n factorial is used to simplify some of the formulas in this chapter. Let n be positive and be a positive integer, then n factorial is defined as n factorial equals 1 times 2 times 3 times 4. Now let's look at an example. Let's say we have 5 factorial. Well, that's the same thing as 5 times 4 times 3 times 2 times 1. Or I could say 5 times 4 times 3 times 2 factorial. Or I could say 5 times 4 times 3 factorial. So I can stop that wherever I wanted to or wherever I needed to. So let's use that information for problem number 38 to see if it helps us to find the limit of this sequence. So we have a sub n equals n minus 2 factorial all over n factorial. So let's rewrite that n factorial to help us to simplify this. N factorial, like 5 factorial, is the same thing as n times n minus 1, one number less than that, times n minus 2, and we'll stop there and use that to simplify our numerator. So now we're finding the limit as n approaches infinity, simplifying that of 1 over n times n minus 1. And if you look at your terms in your denominator, they will continue to get larger and larger and larger and larger with our numerator staying at 1. So that tells me that this converges to 0. All right, let's take a look at a couple more problems here. We have a sub n equals sine n all over n. Again, it may be helpful to rewrite this and look at those separately, see them separately, like so. So now I'm finding the limit as n approaches infinity of sine n times 1 over n. All right, so that 1 over n, that's that same fraction we keep looking at. We know that this approaches 0. Sine n, that bounces between -1 and +1. However, since this approaches 0 and is being multiplied times that, then that tells me that the sequence converges to 0. All right, let's take a look at one more example. Let's find see if we can find the expression for this sequence here. We have 2, second term 8, third term 14, fourth term 20. So if we look at what's common between those, each one of those numbers, we see that we're adding 6 each time. And we'll represent that by calling that 6n. So we know we have 6n plus or minus some constant for this expression. So let's see if we can figure out what that constant is and see if it fits our sequence here. So we know that this is the first term. So if I let n equal 1 plus a, that should equal 2. Now let's simplify and find out the value of a. Subtract 6, subtract 6. So we find a to be -4. So now I'm saying that my expression for this sequence is 6n minus 4. But we can check it out. The first term, 6 times 1 minus 4. 6 times 1 is 6, minus 4 is 2. That checks out. The second term, 6 times 2 minus 4. 6 times 2 is 12. 12 minus 4 is 8. That checks out. And you can check all of them if you choose to. Third term, 6 times 3 is 18. 18 minus 4 is 14. All of those check out, so this tells me that this expression works for this sequence. Now, there is a possibility that you can have more than one expression to work for a particular sequence. Okay, I hope you found this video and those examples to be helpful. Thank you.